This is the fourth CIVO seminar, if I recall correctly, and it's the second last before the summer. So we're going to have another one 2 weeks from now. We haven't decided the speaker yet. As usual, we're very grateful to Morten Bennetsen to get this initiative off the ground, to the whole scientific committee, and to Mandy Chan for making it happen. And I'm very grateful to George and Mike for accepting to present their paper, and looking forward to it. And so the chair is Walter Dessain this time. Over to you, Walter.
Good afternoon or good evening, everybody. So I've been endowed with the chair power. So we're very excited to have Georgiadis here, who's going to talk about A/B contracts. So this is a combination of theory and empirics. And I looked at the slide starting page 24, slide 24, we're going to dive into empirics. So in terms of how we organize this, Mike Powell, which is a co-author, will be trying to answer any kind of clarifying questions on chat. We're going to try to have 2 breaks during the talk, where you're going to be able to ask general questions. So I'm going to try something new here. Is on these questions, you're allowed to raise your hand. So if you want to raise your hand, you have to click on participants. And then there's you can raise your hand and I can then just call on somebody to ask a question. Okay, so we're going to, during these breaks and also in a discussion after 1 hour, we're going to have a general discussion. Just kind of raise your hand if you have something to say. And I think in the chat the questions there will mainly be answered by Mike Powell. So that's going to be the division of labor. George, the floor is yours.
Thank you very much, Walter, Andrea, and the rest of the organizing committee. Thank you all for being here. I'm very excited to talk about this paper, which is joined with Mike Powell, and it's titled A/B Contracts. So it's becoming more and more common that firms use experimentation to learn, for instance, about product design decisions, pricing, advertising, and so on. Now, an area that is critical in the organization and management of a firm is the design of compensation structures and how people should be rewarded for outcomes. This is a very difficult problem to solve, and it's a question that has largely evaded recent trends in data-driven decision-making. So what we show in this paper is that under mild assumptions about the way people respond to incentives and they value monetary rewards, simple experimentation coupled with a few theoretical insights from contract theory can lead us a long way towards optimal contracting. So let me start by motivating what we do in the paper using a very simple example. So imagine that you run a company that sells kitchen knife sets, and you hire teenagers every summer to sell door to door, and you pay them a simple piece rate for doing so. Your expected profits are simply your net profit margin times sales. So in this expression here, M is your gross profit margin, alpha is your piece rate, how much you pay your salespeople per unit of sales, and A is mean sales. What you would like to know is how should you change your piece rate? Should you increase it or decrease it? So let's consider the conceptual exercise where you marginally increase your piece rate. So you change it by a small amount. Then your profits are going to change by this quantity. The first term captures a behavioral effect, namely, how are your profits affected due to people working harder, selling more? And the second term captures a mechanical effect, namely, what is the effect on your compensation costs of increasing the piece rate by that small amount. And ultimately, what you would like to figure out to know is whether this derivative is positive or negative. Okay? Now, to answer this question, of course, you need to know your gross profit margin, M. You need to know your piece rate, alpha. You need to know your mean sales, A. And crucially, you need to know the behavioral response, how sales are going to be affected if the piece rate changes by a small amount. Now, given just observational data, to answer this question, you would need to know what we call the production environment. That is, you would need to know what are your employees' effort costs and how different levels of effort map into sales. Now, you are likely to not know this information, but importantly, you don't need this information if you're willing to run an A/B test. That is, for instance, split your salespeople into a treatment and a control group, and then perturb the piece rate for the treatment group and collect the sales data. And then you can use this data to estimate that behavioral response and determine whether you should increase or decrease your piece rate. Now, what we do in this paper is we want to examine how a principal should improve upon a given contract. And we want to focus on what the principal needs to know, what information she needs in order to perform this exercise, and how should she use that information. Now, the previous example that I showed you sidestepped two critical issues that our approach will have to address. The first is that it restricted attention to linear contracts. Now, when we look at general nonlinear contracts, such contracts can be modified in a continuum of ways. So in principle, one would need effectively a continuum of A/B tests. Why? Because you need to know how productivity is going to respond to every possible modification to the contract. And there's just a continuum ways that you can do that. Our key lemma, and that's going to be the key conceptual contribution of the paper, is going to show that a single A/B test, together with an assumption about the agent's preferences for money, is going to provide all the needed information. Namely, that single A/B test is going to help us pin down how the agent's productivity would respond to every possible perturbation that you can construct. The second limitation of that example is that we asked a local question. Namely, we asked, how is the principal's profits going to change if she perturbs the contract by a tiny amount? In practice, of course, one is interested in non-local changes to a given contract. If not for anything else, because changing the compensation structures at any organization involves some fixed costs. We're going to provide conditions so that a single A/B test suffices to extrapolate the ideas and determine how to optimally adjust a given contract non-locally. So the first part of the paper is going to be theoretical. The latter part is going to be empirical. And what we're going to do is to evaluate the methodology that we develop using a data set from De La Vigne and Pope. In that paper, De La Vigne and Pope conducted a real effort experiment where subjects were tasked with pressing the A/B keystrokes on their keyboard. So they had to press A/B, 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 and so on. And they were paid an incentive payment to do so. What is especially useful, and I think unique in that experiment, is that they have outcome data for several different incentive treatments. So the first exercise we're going to do is to test our model's ability to predict out-of-sample performance. First, let me tell you why this is important, and then I'm going to go into the details of exactly what we do. So if our model is going to generate good modifications to a, say, status quo contract, it better be able to predict output in out-of-sample contracts accurately. So in this exercise, we will take every pair of treatments that are available in that data set, and we will take that pair to be our A/B test. And we will use the data from that A/B test together with our model to predict performance in the remaining treatments. And then we will compare the predicted performance to the actual observed performance. We will find that the correlation between predicted and actual performance is just over 0.9, and the mean absolute percentage error is just less than 2%. as a benchmark or a point of reference, if you will, the performance varies about 18% across treatments. That means that the maximum effort, the maximum performance across these treatments is 18% higher than the minimum average performance. The second exercise that we're going to do is to assess the performance of the adjusted contract that is generated by our procedure. So we will use all the 7 incentive treatments which are available in that data set to construct a benchmark model, which is akin to the principal knowing the entire production environment. And then using that benchmark, we will compute the optimal contract. This is what the principal would put in place if she knew all the parameters that are payoff relevant. So we will be solving the problem of Grossman and Hart or Holmstrom and so on. Then we will use the data from every one of the available A/B tests. So we'll take any arbitrary pair of treatments. We will use the data contained in that pair to compute a test optimal contract. And then we will compare the profits of the test optimal contract to the profits of the benchmark optimal contract, which is, again, what the principal would put in place if she knew the true model and not just have the limited information. On average, we will find that the test optimal contract attains just over 2/3 of the profit gap between the status quo contract, that's the original benchmark contract, one of those treatments in the Lavigny Pope, and the benchmark optimal contract. So the test optimal contract, in other words, takes us 2/3 of the way to an optimal contract. That is what we're going to show in our empirical exercises. So in the interest of time, I'm going to skip the related literature and jump straight into the model. So we will have a principal agent model akin to that of Holmstrom 1979, and the timing is going to be as follows. The principal is going to offer a contract W that is going to be a mapping from output into payments. The agent is going to observe that contract W and then choose an effort A. And then output X is realized according to some probability density function F, conditional on effort, and then the parties' payoffs are going to be realized. We are going to normalize effort such that the expected output conditional on a given effort level is equal to that effort level. We will assume that the agent's utility is additively separable in money and effort. The function V is the agent's utility function, and it satisfies the usual assumptions. So it's strictly increasing and concave. And the cost function, again, satisfies the usual assumptions, which is it's increasing and convex in effort. The principal's profit, pi of W, is equal to the principal's revenue. So the principal's gross profit margin times expected output, which is simply equal to effort, minus the compensation costs for the agent. When I write A of W, what I mean is the effort corresponding to a given contract W, and in the next couple of slides, I'm going to show you exactly how it is derived. Now, let me tell you what the parties know. So we will denote by P the production environment. The production environment is a pair which consists of a family of PDFs that map every level of effort into output and a cost function. We will assume that the agent knows the production environment. The principal, however, she knows the agent's utility function, and she has access to outcome data from two contracts, a status quo contract WA and a test contract WB. Specifically, the principal knows the PDF that corresponds to the two effort levels associated with these two contracts, but she doesn't know the agent's cost function or the PDF corresponding to any other level of effort. We will have to assume that the agent knows the principal knows the agent's utility function. When we do the empirical exercises, we will test the sensitivity of our results to this assumption. We will find that our results are essentially invariant to the principal's assumptions about the agent's utility function. Let me tell you a little bit about the agent's problem. So given a contract W, the agent is choosing his effort to maximize the usual expected utility minus his effort costs. If the agent works a little bit harder, then he makes some outputs more likely and some outputs less likely. That's this F sub A thing. This is the derivative of the PDF with respect to effort. So the agent is going to work harder if the output levels that he makes more likely are the ones that are well compensated under the given contract W. And if the output levels that he makes less likely are the ones that are poorly compensated. So the correlation between the agent's monetary utility and which outputs become more or less likely, this is what we'll call the agent's marginal incentives. And it's this display equation that you see here. Throughout, we're going to assume that the first order approach is valid, and therefore the effort that maximizes the agent's utility for a given contract is implicitly defined by this first order condition. So the agent is going to equate his marginal incentives to the marginal cost.
George, can I just,
Yes.
There's a couple of clarifying questions.
Absolutely, yes.
First one by Willy Fuchs. Could you ask your question, Willy?
Yes, hi. My question was, do the agents, I mean, it's a little bit more conceptual in general, but do the agents understand that their actions or outcomes during this test phase will have long-term consequences? And
Good.
we worry about that.
So throughout this paper, we take the A/B test to be as given. So we take that data to be given and to be pure. That is, they're not contaminated by any sort of ratchet effects. We absolutely do worry about that, but I think this is something to be explored in a separate study. So throughout, that's a good question. Throughout this paper, we're going to take the A/B test to be as given. There's no decision to be made or any choice to be made associated with designing that A/B test.
Elliot Lipnowski had a question if there's a specific or conceptual reason to think of V as more a priori knowledgeable than C. Perhaps V is more transferable across work contexts.
Absolutely, yes. That's one. When I go into the analysis, I think it will become clear that if you want to assume that the principal knows C, ultimately she's going to use that information to back out V or to make an inference about V. So V is the object that is crucial for the principal to know.
Andrea, do you want to ask your question?
Mike already replied on the chat. Thank you.
Thank you.
So I told you about the agent's response. Now let me tell you about the principal's problem. So the principal's goal is to choose a profit maximizing contract that gives the agent at least as much expected utility as the status quo contract. So we implicitly assume that under the status quo contract, the agent's participation constraint is binding, and therefore any modified contract must give the agent at least as much utility. So the principal wants to solve this maximization program. So in the first line, you see the objective. The principal wants to maximize his profit, subject to the agent's participation constraint. And you see that we have already put in here the fact that the agent's effort A depends on W. Okay, so let me give you an outline of how I'm going to proceed. And then I'm going to dive into some slightly tedious analysis, but I have to go through that to explain the ideas. So first, we're going to consider local adjustments. What we mean by local adjustments is that we will restrict the principal's attention to contracts which are close to the status quo contract in this normed sense. And we will ask, how can the principal find the optimal adjustment? What we will show is that a local A/B test, which I'm going to define, provides all the needed information. So you just need one local A/B test. And then I'm going to go and consider non-local adjustments. That is, we'll consider the full set of contracts which do not have to be close to the status quo contract. And we're going to provide conditions such that the logic from the first section can be extrapolated. And we will show that an A/B test suffices to find an optimal adjustment. And then we will present the empirical exercises. Now,
so let me take a little break to see if there's any general questions here. I think we're going to dive into the model here. So this was the motivation section and the overview. Rahul Depp?
Yes. Hi. Sorry, I just had a quick clarification question about you guys using the first order approach. So, I mean, presumably, there are known sufficient conditions under which that approach works. Do you guys, I mean, maybe this is the wrong time to ask this, but do you guys know in the experiment if the distributions that you guys get satisfy these conditions? In other words, should I be concerned about the fact that you have that first order approach assumption sitting in there?
So in general, those conditions depend on the utility function of the agent and on F.
Yes.
In the way we are going to construct those distributions in the experiment for our, let me try to respond to the question, and it might not make sense to everybody. This first order approach is going to be valid in our approach. When we consider the fully the benchmark model, we will not be assuming that first order approach exactly because we're worried that it might not be satisfied. I'm going to be more precise when I get to that section.
Okay.
When we talk about limited information, we cannot assume that the first order approach, we cannot provide sufficient conditions such that the first order approach is valid because those conditions depend on unobservables. Does that make sense?
Mm-hmm.
Sort of? Okay.
Any other questions? Okay, George, you can go on.
I had a question.
Oh, Andrea.
Just a brief one. You can postpone it to later. So here, one of the assumptions is that there is one agent. In practical problems, we probably will have a distribution of agents.
Good.
How does that matter for the framework?
Okay, very good. That's a very good question. So in one of our extensions, we look at a case in which the principal employs multiple agents who have heterogeneous costs. And we show how our methodology can be adapted. Under some fairly strict, strong assumptions, it suffices for the principal to look at the average. So the principal does not have to distinguish between agent types. If those conditions are not satisfied, then you have to look at type by type. Very short answer, the methodology is easy to adapt. What you would need to know is information about the individual types. So you would like to be able to assign agents into types. And then you, when you adapt the contract, you have to look at, you have to consider the average effect and not just one effect. Does that make sense?
Thank you, George. You can go on now.
Okay, thank you. So I'm going to define a piece of notation. And the reason is because we will want to articulate the question of how should the principal locally adjust the contract. Okay? And we will have to be able to say how things change, how the agent's effort, how the agent's utility, and how profits change as we change the contract. So because a contract is an infinitely dimensional object, we'll have to use a more general notion of a derivative to think about this problem. So for a given contract W and a given function Q of W, we're going to define what's called the Gateau differential in some direction T. And the differential is defined in this way. What this differential is saying or is measuring is how the function Q, when it's evaluated at contract W plus theta T, and T is some arbitrary function, changes in theta for theta around 0. So now I'm going to be looking at the agent's responses. So I'm going to explore how the agent's effort and the agent's utility change if we replace a given contract W with another contract W plus theta T where theta is close to 0. What theta close to 0 does is that it ensures that the new contract is close in that norm sense that I showed you earlier to the original contract. And this lemma is the key conceptual contribution in the paper. It says that locally adjusting a given contract W in some direction T changes the agent's effort by this amount. The numerator is the change in the agent's marginal incentives when we adjust the contract in the direction T. So the change in the agent's effort depends on how the adjustment affects the agent's marginal incentives and on the curvature of the production environment. And second, the agent's expected utility changes by this amount. Now, here I want to make two observations. The first is that the ratio dA over dI does not depend on the adjustment T. And that's going to be important in what follows. And the second point is that this ratio, as well as the change in the agent's utility, does not directly depend on the agent's cost function. And this is important because the principal doesn't know the agent's cost function. Now, moving to the principal's problem, the principal's expected profit under contract W, I've already defined to be given by this display equation here. So now let's consider the conceptual exercise where we adjust a given contract W in some direction T. And when I say we adjust a given contract, what I mean is that we replace the contract W with a contract W plus theta T, where theta is some constant close to 0. Now, profits change according to this Gateau differential. The first term here captures the change in the principal's profit due to a change in the agent's effort. That's a behavioral effect. And the second term captures the change in the principal's profit due to a change in the cost of compensating the agent, meanwhile holding effort fixed. So when the principal is considering small adjustments, infinitesimal adjustments, then her objective can be formulated by this maximization program. So the principal is looking for a direction T in which profits increase at the fastest rate, subject to the constraint that the agent gets at least as much utility as under the status quo contract. Now, adjustments have both a direction and a magnitude. We normalize the magnitude to focus on the direction. And this is what this norm constraint is imposing here. Okay. So what does the principal need to know to solve this problem? So to do that, it's going to be useful to write down the principal's problem in terms of primitives. So this is the principal's objective, and this is the agent's participation constraint, namely that any adjustment gives the agent at least as much expected utility as the status quo contract. And lemma 2 is going to show that the relevant aspects of the production environment for solving this program are three things. The first is that the principal has to know the PDF of output corresponding to the effort in the status quo contract. She has to know F sub A, how this PDF changes as effort changes on the margin. And crucially, she has to know how the agent's effort is going to respond if the status quo contract is modified in any direction. And I want to emphasize here that this is a big set because there is a continuum of feasible adjustments that could be done to the contract. I'm not going to show you the formal statement of this lemma because to do so, I would have to introduce a lot of notation, which I think is going to be counterproductive in a presentation. We will argue that if the principal knows F sub A and the change in the agent's effort for some arbitrary adjustment T, then this information is going to suffice to evaluate the change in the agent's effort for every other adjustment T prime. And to do so, we'll be using the lemma that I showed you 2 slides ago. So let me now define what we mean by an A/B test, and we'll define this new object, which we will call a local A/B test. So an A/B test for 2 contracts, say WA and WB, is a pair of PDFs. The PDFs corresponding to the effort induced by each of these contracts. We will define a local A/B test to be a triple, which comprises of the following objects. The first is the PDF corresponding to the effort under the status quo contract. The second object is the marginal change in that PDF as effort changes. And the third object is the marginal change in effort as we move from the contract WA to the contract WB. The way one can interpret a local A/B test is that it comprises data for a status quo contract and a limiting contract, which is arbitrarily close to the status quo contract. And we're going to assume that this that the marginal change in the agent's effort is not equal to 0. Intuitively, this is saying that the local A/B test is informative. If the agent's effort doesn't change when we modify the contract, then we cannot make any inference about other adjustments. So this is the main sufficient statistic result for the first part. So the principal wants to solve this optimization program, which I showed you earlier. And proposition 1 shows that the information provided by a local A/B test suffices to solve this problem. Again, I'm not going to show you the formal statement. It is in the actual paper which is posted, but I'm going to give you a heuristic derivation of why this information is sufficient. So knowing F sub A, the principal can evaluate for every adjustment T, the marginal change, the change in the agent's marginal incentives. And that is because she knows T, she knows V prime by assumption, and the A/B test allows her to, gives her information for F sub A. Second, and crucially, knowing F sub A and the marginal change in effort, the principal can use this identity to evaluate for any adjustment T, how effort is going to change in response to that adjustment. And this is where we use the fact that the ratio of dA over di is not dependent on the adjustment itself. Okay. So knowing this quantity and this quantity allows us to pin down how the agent's effort changes in response to any adjustment to the contract. And finally, knowing the PDF under the status quo contract, the principal can evaluate the effect of an adjustment to her compensation costs, namely the second term in the objective here, and the participation constraint. And therefore, the principal has all the needed information to solve this maximization program. This program is a standard convex optimization problem, so it can be solved using standard techniques. I'm not going to show you the solution, it's in the paper. Proposition 2 gives the characterization of the optimal local adjustment and also gives a condition for the status quo contract to be locally optimal. That is, for the best adjustment to be to not adjust the contract at all. So this is what I wanted to say about local adjustments. And now I want to move on to non-local adjustments. Of course, in practice, A/B tests are not local. You don't have an A/B test for contracts which are infinitesimally close to each other. And firms are interested in non-local adjustments. Now, in general, if you want to find the optimal non-local adjustment, you have to know the entire production environment. You have to know how every level of effort maps into output, and you have to know the agent's cost function. We're going to provide 2 conditions, which are going to allow us to extrapolate the ideas from the previous part to assess such adjustments using just an A/B test. The first condition specifies or requires that the output distribution is affine effort. That is, for any effort A, there are two functions G and H such that this identity is satisfied. Now, this condition is useful in several ways. The first is that if we have an A test, which recall comprises of the PDFs corresponding to the efforts under two contracts, then we can pin down these two functions G and H, and therefore infer the PDF of output for every level of effort. And second, this function H is simply the F sub A, which recall is instrumental in much of our analysis so far, specifically in the agents problem. And this F sub A is now independent of the agent's effort, and therefore the marginal incentives corresponding to any given contract can be written in this form, and the specific point to observe is that they do not depend on the agent's effort. So I see Willie has a question. Should we take it?
Let's wait until slide 24.
All right. The second condition we will assume is that the agent has isoelastic effort costs. That is, the agent's marginal cost of effort is given by this equation for some parameters beta and epsilon. What this condition implies is that for any given contract W, the relationship between the agent's effort and the agent's marginal incentives is given by this log-log relationship. And given an A-B test, one can evaluate the marginal incentives for any given contract W. And then we can also evaluate the effort corresponding to the two contracts, since effort is simply the corresponding expected output. And therefore, the principal can pin down beta and epsilon, and therefore predict the effort for any contract W. Now, moving to the principal's problem, the principal's profit, if she offers a given contract W, is given by this expression. And this is an expression you have seen before. The only difference being that I have substituted these functions G and H, which the principal can pin down using an A-B test. Given a status quo contract, therefore, the principal wants to choose a new contract W, which maximizes her expected profit, subject to the agent's participation constraint. And proposition 3 shows that the information that is contained in an A-B test suffices to solve this problem. Now, just conceptually, remember that an A-B test allows us to pin down G and H, these two functions, and allows us, using the two conditions in that log-log relationship, to predict the effort corresponding to any new contract W. Moreover, using the second condition, we can pin down the cost parameters beta and epsilon, and therefore evaluate the agent's expected utility under any given contract. So this explains why the information provided by an A-B test is sufficient to solve this problem. And this problem can be solved in the typical two-stage Grossman and Hart approach. So in the first stage, we fix an effort level A, and we look for a cost minimizing contract that implements a given effort. And this is a standard convex optimization program. In the second stage, we're going to find a profit maximizing level of effort. This second stage problem is notoriously difficult and ill-behaved. It's typically not a convex maximization program. However, numerically, it's one that's easy to solve because it's one-dimensional.
Okay. So let's take maybe a break here, since I think we've gone through the main theoretical analysis. Let's first take Willy Fuchs, then Wendelin, and then Rahul.
Yeah, hi George. So the question is, and I guess it's partly how do you want us to take them all apart? So I can see it two ways. One is say, look, this is how powerful A-B and A-B tests are. The alternative is to say, look, this is how strong a condition I need for those to be actually useful, or so so generally useful. It seems to me that a lot of the conditions are actually very strong.
Absolutely.
So maybe had a bad night and I'm on the negative side this morning, but I take more of this to say, look, for A/B tests to be really that useful, we need these very strong conditions. And if that's the message, then it would be nice to have like this proposition 3 more like a necessary, right? So for A/B tests to work in general, these are, these properties that you said are kind of necessary, or have a sense of that, versus if you want to sell the opposite, maybe it's a different type of proposition. I don't know if I'm clear.
So I agree that these conditions are strong. I think there's 2 ways to interpret them. One is that if these conditions are satisfied, then our results are going to be exact. And indeed, of course, these are very strong conditions, and it's ultimately an empirical question whether they're satisfied. The second way to think about them is that these conditions are true if we are looking at local adjustments, and they are approximations when we look at non-local adjustments, and they become worse and worse approximations as we move away from the status quo contract. At the end of the day, we prefer to be agnostic about that issue. And this is why we have the empirical part in the paper, where we will basically test these conditions and to what extent they're useful in predicting performance and generating good adjustments, which I'm going to define in due course.
Wendelin?
Yeah, so as I understand it, the A/B test kind of helps the optimizing person here to figure out information, but information that is, if I understood correctly, also available to the agent himself. So I wonder, I mean, this may be an old school question, but I wonder, normally people used to do like menus of contracts or message dependent contracts in order to do that. So what's the relationship there? Is this something that would also work or not, or yeah?
So that's a good question. There's some literature that has taken that approach, namely that there are some unknown parameters that the principal is trying to estimate, and he's going to use some sort of a direct mechanism to elicit that information. We take this orthogonal approach because in general that literature focuses on usually a single or 2 parameters which are unknown. And if you want to have a richer space that is unknown to the principal, it's quite difficult to think about that in terms of parameters.
Rahul?
Yeah, so I just had one question. This is probably might be nonsensical, but let me just ask it anyway, since I can't go back in your slides. So given that you guys, so earlier on in the talk, you didn't make these functional form assumptions. So I guess I'm going back to one of Andrea's earlier question, which is if you guys are taking a little bit more of a stand on what these distributions look like, do you always need still the full distributions, or can you make slightly stronger assumptions and then be able to make the same inferences from fewer moments of the data? So am I making sense?
Yeah, no, that's a good question. In general, the only case in which you only need, so you only need the first moment if you assume that the principal is risk neutral and you consider linear contracts. Anything beyond that, you need the specific distribution. Whether a finite set of moments suffices, I don't know the answer to that question.
So let's postpone other questions to the end of the talk. George, you have 15 more minutes to conclude, but if you...
Sounds good. Thank you very much. So now let me move to the empirical part. So the goal of this section is to assess the performance of our model. And like several of you observed, we make some strong assumptions. And it's ultimately an empirical question whether they are satisfied or to what extent they're satisfied. So for this purpose, we're going to use a data set from De La Vigne and Pope. Specifically in that paper, they ran a real effort experiment on the Amazon Mechanical Turk, where subjects were tasked with pressing the A/B keys on their keyboard for 10 minutes. And they were given different financial incentives to motivate them to press those A/B keys very fast. So they had to press A/B, A/B, A/B key successfully for 10 minutes, and they got paid based on how many times they pressed the A/B keystrokes alternatingly. So what's especially useful and we exploit in this paper is that in that experiment, they have outcome data for 7 different monetary incentive treatments. So for example, in the first treatment, subjects simply got a show-up fee of $1. So these numbers are denominated in cents. Then they have 4 treatments where subjects received a piece rate. So they got a $1 piece rate, and then they got a $1 show-up fee plus a piece rate for each point that they scored. And each point is every time they press the A/B keys successively. So in the first treatment, they got a cent for every 1,000 points that they scored. In the second piece rate treatment, they got a cent for every 100 points they scored. In the third treatment, they got 4 cents for every 100 points they scored. And in the fourth piece rate treatment, they got 10 cents for every 100 points that they scored. They also have 2 bonus treatments where subjects received a $1 show-up fee plus 40 cents if they were able to score more than 2,000 points in that 10-minute interval. And the last treatment, they got an 80-cent bonus. The third column shows you the average points for each given treatment, and that's going to be our X. And the last column shows you the sample size. Subjects were assigned to different treatments randomly, and they participated in a single treatment once. So this is the data, and we're going to use it to perform 2 exercises. The first exercise is going to be to assess the ability of our model to predict performance out of sample. Now, this is useful because if our model is going to generate good modified contracts, it had better be the case that it can predict, given an A/B test, how performance in different contracts is going to vary. So what we do here is that we use the data from each pair of available treatments, and we use that together with our model to predict the mean performance in the remaining treatments. So in other words, say, for example, we take treatments 2 and 3, we take the data in those treatments, and we're going to use our model to predict performance in treatments 4, 5, 6, and 7. And we'll do that for all available pairs. And then we're going to compare our predictions to the observed performance. The second exercise is going to be to assess the performance of optimal adjustments. So first, we will use all 7 treatments to construct the production environment. That is, to construct what is our best fit for the true set of PDFs that map effort into output and the agent's cost function. And then using this production environment, we'll compute what we call the benchmark optimal contract. This is the contract that the principal would put into place if she knew the true production environment. And then for each pair of treatments, we will take that pair to be our A/B test, and we will use the data from that A/B test to compute the test optimal contract. And then we will compare the profit of that test optimal contract to the status quo contract and to the benchmark optimal contract. And we'll try to see, we will see how close do we get to the benchmark optimal contract. This is if the principal knew the true model. Okay. So let me describe the procedure for the prediction exercise. We're going to assume that each subject has a utility function that exhibits constant relative risk aversion. And we'll assume that the coefficient of relative risk aversion is 0.3. We will test how our predictions vary with this assumption. It will turn out that essentially it doesn't vary. It's quite invariant. Moreover, we will normalize effort to be the effort corresponding to any given treatment to be equal to the average number of points in that treatment. Then we will take an arbitrary pair of treatments, which we will label WA and WB, and we will assume that that's our A/B test. And then we will use a kernel estimator to construct the corresponding PDFs of output. Then for every treatment C, and C is any treatment from 2 to 7, we are going to compute the marginal incentives corresponding to that treatment using the data from the A/B test. Specifically, we're going to need this H function. Recall that this H function is the change in the PDF. And this is given by this equation here. Then, using that log-log relationship, we're going to estimate the cost parameters, epsilon and beta. Epsilon is the elasticity of effort with respect to marginal incentives. And then for every treatment, other than the treatments in our A/B test, we're going to predict performance using this log-log relationship.
George, sorry, can I ask a quick clarification?
Sure, yeah.
I don't understand. So the first treatment had no incentives, right? So how do we fit the fact that they are actually putting effort?
Very good. So in the prediction exercise, we will be not considering that first treatment. We will only use that treatment to construct the benchmark model in the latter part, in the second exercise. And that's the reason why we omit it is exactly because it provides no incentive. So we need to enrich the model in some way that I can discuss later, how to accommodate that. So I'm going to focus on A/B tests where the two contracts belong to the same class. I'm also going to talk a little bit about what we call hybrid A/B tests, where the two contracts do not belong to the same class. So let me illustrate the results. So what this graph illustrates is it's going to compare the actual average performance to the predicted performance. So the x-axis illustrates the actual average performance, and the y-axis illustrates the predicted performance, and the dashed line is a 45-degree line. So let's focus on these three red stars. Okay? So how do we construct each of these stars? So let's take an A/B test that comprises of treatments 2 and 4. Now we will use the data in those two treatments to predict effort, to predict performance under treatment 3. And that's going to give us one of the stars. And we do this for the A/B test that comprises of treatments 2 and 4. Then for the A/B test that comprises treatments 2 and 5, and the A/B test that comprises treatments 4 and 5. And this gives us these three predictions. And this is for the A/B, we use A/B tests that comprise of piece rate treatments to predict performance in other piece rate treatments. And the fact that all these stars are pretty close to the 45-degree line implies that the predicted performance is close to the actual performance. A perfect prediction would be spot on that 45-degree line. Another thing I want to emphasize is that performance varies quite a lot across treatments. So you see here that performance in this treatment is about 18% higher than performance in this treatment. We can do the same exercise when we use A/B tests that comprise of piece rate treatments to predict performance under bonus treatments. And this generates these blue triangles over here. What you see here is that our model systematically underpredicts performance in those bonus treatments. I don't have the time to get into exactly why in the talk, but we actually do discuss it in the paper. We can do the same, a similar exercise where we use the two bonus treatments to predict performance under the piece rate treatments. And this is what's depicted by the green circles. And this is perhaps surprising in the sense that we use data that comes from two bonus treatments, and we try to predict performance under a totally different contract, namely a linear contract. Another thing I want to emphasize is that the predictions are similar no matter which A/B test we use to generate them. And this is evidenced by the fact that for every treatment C, the predictions are tightly clustered. This is something else that we found a bit surprising. So in this table, I want to show you three more things. So first, for homogeneous A/B tests, that is A/B tests where both contracts belong to the same class, the correlation between the predicted and the actual performance is 0.94. The mean absolute percentage error is just less than 1.6%. And perhaps surprisingly, the worst case prediction, the worst prediction across all of them, is within about 3.34% of the actual performance. We can do the same exercise for hybrid A/B tests. That is, look at A/B tests where one one contract is a piece rate treatment and the other contract is a bonus treatment. Here, the correlation is a bit smaller. It's 0.84, and the mean absolute percentage error is a bit above 2%. However, the worst case absolute percentage performance prediction error is 10.7%. That is, the hybrid A/B tests sometimes generate quite poor predictions. And again, I don't have the time to discuss this online, but we do discuss it in the paper. So I urge you to take a look at that.
George, just in terms of time, you have at most 5 minutes.
Okay. One more thing is that the prediction accuracy is quite insensitive to the coefficient of risk aversion. And you see here that both the correlation and the percentage errors don't vary much. And in fact, the accuracy is very similar if we assume a quadratic utility function. Now let me talk about the second exercise. So we're going to use all 7 treatments to construct the production environment. Now, let me tell you a little bit about how we do that. So for constructing the family of PDFs that map effort into output, for every level of effort, which corresponds to the average, to the mean performance for one of the 7 treatments, we use a kernel estimator to construct the corresponding PDF in the same way as for the previous exercise. And for every effort that is not in that set, we use a spline interpolation to construct the corresponding F. Then to construct the cost function, we're going to assume that it comprises of this isoelastic component for some parameters C naught and P. And it also has this additive constant term I naught. And the goal of that term is to capture the point that Willie made earlier, namely that in our first treatment, subjects did not get any incentive payment. So if we were not to incorporate such a component, that would assume that, that would imply that effort should be 0, which of course is not. So what this term can capture is incentives due to things other than direct monetary incentives. For example, in the real world, we are motivated not just by financial incentives, but by prestige and the scope for a promotion, peer pressure, all those kind of things. In the experiment, maybe the subjects cared about a good review, or they cared about, it was just fun, say, to try and see how many points they could score. Then we assume that the agent's utility satisfies constant relative risk aversion, and then we fit these 3 parameters using nonlinear least squares. Then we assign a given marginal benefit to the principal and marginal revenue to the principal of each point. And for every treatment C, we compute the profit maximizing contract that gives the agent at least as much expected utility as the treatment WC. And we denote the profit of the benchmark optimal contract by pi star. Then we compute the optimal adjustments. So we will take an arbitrary pair of treatments, which we will label WA and WB. And using the same procedure as in the prediction exercise, we construct the 2 PDFs and the cost parameters. And for every treatment C, we compute the test optimal contract that gives the agent at least as much utility as WC. And then we go back to the constructed production environment and we evaluate the profit of each test optimal contract, which we denote by pi superscript AB. Now, how do we evaluate performance? We will define the maximum available gains to be the difference between the benchmark optimal contract and the profits of the treatment C. And the average realized gains is when we average out the realized gains across all homogeneous tests vis-a-vis the benchmark contract. And when we average across the treatments, we find that the average realized gains are about 68% of the maximum available gains. And this ratio is actually quite insensitive to the different choices of M, the principal's marginal revenue, and the coefficient of relative risk aversion. Now, Wouter, do I have 2 minutes to go over this illustration?
Okay, 2 minutes.
Okay, thank you. So
and then
what
you
I'm
should
gonna
wrap up after that. Yeah.
Yeah, I'm gonna wrap up. This is the last slide I want to talk about. So in this figure, I'm going to illustrate and compare the maximum available gains to the average realized gains. So this is the maximum gains are plotted on the x-axis, the average realized gains on the y-axis, and the red dashed line illustrates the 45-degree line. So each of these stars illustrates the average realized gains vis-a-vis the maximum gains when you are trying to give the agent at least as much utility as treatment C. So one thing to notice is that the maximum available gains vary quite a lot. So for treatment 2, the maximum available gains is about $35, and the principal is able to achieve almost all of those. And this is evidenced by the fact that this is close to the 45-degree line, which is in a way the holy grail. On the other hand, for treatment 7, this is already close to optimal, so the maximum available gains are close to 0. Now, when you eyeball these these blue stars, what you see is that they're similarly close to the 45-degree line. And to illustrate this, we have run in a least squares linear regression. And what you see is that the slope of this line is about 1, and the gap and the intercept is about -3. What this means is that the average gains are about $3 smaller than the maximum gains. Now, why can the principal not get to the optimal contract? In general, this is because she is overpaying to implement a given effort level, and she is implementing a given effort level, and she's implementing not the profit maximizing effort level. In the paper, we elaborate on that discussion. Basically, this $3 gap is roughly half-half due to those two effects. So this is what I want to say. I'm going to skip a couple of slides. This is the decomposition, and this is how we do on delivering on our promise to give the agent at least as much utility as the status quo contract. I'm going to skip the extensions and wrap up. So I'm happy to take any questions. I'm sorry I went a bit over time. Thank you very much.
Okay, so for the questions, you can raise your hand or also just unmute yourself. So why don't you just go over your summary of future work, George? In the meantime, I think the questions will bubble up.
Okay, sounds good. So we view this as a first step towards what we think can be a quite fruitful agenda. I think we just scratched the surface of what can be done. Some of the interesting questions are first to deal with the statistical and the approximation error. In practice, you have a finite sample size, and therefore when you estimate a given PDF or you estimate parameters, there's some error. So dealing with that error and what that implies for the optimal adjustment is something to be further explored. A second big thing has to do with designing the A/B test. Throughout, we took the A/B test to be given exogenously. Of course, that is often a decision to be made. And in designing an A/B test, one should also think about potential manipulation, which is something that Willie brought up earlier, for instance, ratchet effects. Conceptually, the ideas from this paper can also be applied to think about intertemporal incentives. But now one would need a slightly richer set of data to be able to back out how people trade off today's incentives versus tomorrow's incentives. One can also think about designing incentives for teams of workers where you don't have an individual performance measure, but rather you have an aggregate measure.
George,
again,
I have
these
a
are
few
just-
questions.
Yep.
Willie? Willie Fuchs?
Yes, sorry, I was just unmuting myself. So one question on the data to understand how you're using it and if you're getting all the power perhaps that you can out of it. So you're literally taking it as 6 data or 7 data points, like just using the averages, because I mean, literally nobody was subjected to 2 treatments, right? So everybody had only 1 treatment. So you're sort of considering the average person, if you will. But presumably you have some distribution within a treatment, right? And if you try to fit some family of distributions over preferences or something, then, if you say the population has some heterogeneity, right, to explain 1 treatment, then now you can use, all the 500 data points of the other treatment to see if it works like in your model, because or I don't understand. Are you just using 6 data points, and is there no way in which you can try to use more? Or
Okay, so to be clear, we use all the data points. So all the samples for each treatment to construct the corresponding PDF. So we're not just using the average, we use all of them. You are right, however, that we treat all subjects as being identical. In the paper, we have an extension in the appendix where we basically show that if the 2 conditions that I showed you earlier, namely that the PDF of output is a finding effort and the worker's effort costs are isoelastic, and third, the agents are heterogeneous, but they all have the same elasticity of effort with respect to marginal incentives, then it suffices to just look at the average, to not just bucket workers into types. We could do something along the lines of what you suggested, namely to treat them as heterogeneous, but to do so, we would have to assume an explicit distribution over types. And because the subjects participated in a single experiment, in a single treatment once, that would be quite arbitrary, I think.
Heskey?
So this is a little off to the side of what you have, but a bit in spirit of Andrea's question of having enough people and things like that. So here the assumption is people perfectly understand, agents perfectly understand everything. And for people who are playing only once, that can take a while to learn. So an aspect of A/B design that might be relevant if I'm thinking about knife salesmen is, how long do I run this for? Like, do I allow these guys to figure out for themselves how effective that contract is on them, or whatever it is?
So for the purposes of the knife salesman, you can think of the period as being a summer, and we just take some people in some neighborhoods and give them some contract, and some in another neighborhood and give them some other contract. We compare the performance this year and adjust it. Yeah.
But more generally, that's going to be a design element that requires thought as well.
Yeah, absolutely. Absolutely.
If we have a
final
minute,
questions? Bob.
I'm unable to raise a blue hand as a co-host. They don't tell you that when you sign up. So costs and benefits. So I would think about boundary conditions. I have Holmstrom incentive systems in my head, and I have, I guess, for example, Blader, Gartenberg, Pratt in my head. As I look at this list of extensions like ratchet effects and especially dynamics and Andrea brought up multiple workers, but teams is almost a different word in that it connotes to me sort of more interaction among those workers rather than just heterogeneity across maybe separable workers or something. What I'm worried about in all those cases is kind of unmeasured heterogeneity. What if I can measure only a piece of the incentive system? So, what's the equilibrium among these workers? and you could tell me, no, that's part of what we'll estimate, but then what if when you do your A/B testing, you change that equilibrium, right? So, I think knife salesman might be a good example, and trying to articulate both what you would need to be able to measure in these richer settings, and as a result of the difficulty of that measurement, boundary conditions on where this will really get applied, I think would be productive.
Good, thank you. That's a good point.
Andrea also has another question.
Yeah, I think this is amazing. This is extremely useful and useful theoretically to clarify what we should be doing, and also useful empirically. I have more of a suggestion to kind of show how useful it is. So what's your competitor? In a sense, one thing companies could do is to have theory-free optimization. So they have the status quo, they run another experiment, so on and so forth. And they can do this, if they do that, they can do it, they modify the W function, and then they can use standard optimization techniques they will consider W some kind of vector, and they will make some assumption on smoothness and use these optimization techniques. So it would be interesting, I think, to compare, and I think those methodologies would do very poorly here, because in order for them to work well, you would need I think my guess is you would need a lot of data. You would need a lot of data points. And so what it would be nice, this is just a suggestion to kind of have a race between your methodology and these theory-free approaches, and see how much better your approach does.
So one thing that is a little bit so yes, you would need a lot of data, but you would also, I think, need a lot of different treatments to kind of assess, like, okay, we change the contract in this way, what happens? So we are basically using kind of 2 points, and then we're fitting our model there and then extrapolating beyond. And of course, like, every model fits 2 points. And so there's going to be a lot of external validity issues, I think, when you use a model-free approach. Now, that said, there are maybe other smarter ways to use the data from the 2 treatments to predict what would happen across all other treatments. And that's something that we should look at.
Yeah.
Okay, thank you. Oh, George, go ahead. Last words.
Andrea, do you have any references in mind?
No, I can try to think about something. I think there would be, if you search like A/B testing, there may be some standard optimization techniques on where you should look next and stuff like that. Because A/B testing is used in situations where there is no agency problem,
right?
And so you could take inspiration from that.
Okay. Thank you, everybody. This was a great participation, great questions, and especially a great presentation by George, and great comments by Mike on the chat box. So it's officially over, but if you want to hang out and chat with George, feel free to hang out a bit longer and ask individual questions, or have your lunch. Thank you, everybody.
Thank you very much, everybody.
Thanks.
Thank you.